Mr. Covey here, and this video and this whole learning check in general are just going to directly build off of last learning check. Okay, so we're still talking about rational functions. Everything you learned before about vertical asymptotes, horizontal asymptotes, domain, zeros, all that stuff still applies. All we're going to do in this learning check is layer on a few more important features. And you're like, why do I need to know more things about rational functions? The idea is it's going to prepare us for our last learning check, which is on limits. Okay. That last learning check is really kind of like a thing to get you ready in case you take a calculus course in college. Cool. So just going to get you ready for that. So what I'd like you to do first is one of these problems from last learning check. Here's our rational function. I want you to fill all this stuff out. Remember, first step is factor, 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 factor. Okay. So start by factoring. Cool. I'm going to pause, give you a chance to do that. We'll go over that. Something weird happens here, and I want to discuss that. That's going to be kind of a new thing. Give it a try. Actually, pause, give it a try. Thank you, thank you. Okay. So if you've been kind of sticking with this last learning check, you probably filled out the characteristics like this. So you looked at the denominator and you said, I got an x plus 3. So the denominator is going to tell us about vertical asymptotes. So I'm going to have a vertical asymptote where x plus 3 equals 0, which is that x equals negative 3. And if I got a big old vertical asymptote at x equals negative 3, then my domain is going to be everything except for that. I don't have a horizontal asymptote because my degree, my exponent in my numerator is one more. It's more than the degree of the denominator. My zeros are when the numerator equals 0, just at 4, positive 4, negative 3. And to figure out the y-intercept, I just plugged in 0 and got out negative 12 divided by 3, which is negative 4. Now, there's actually some aspects of this that are wrong. Okay, just two things, but the reason that they're wrong is there's something that happens when you look at this that we haven't seen yet. Okay, and if you just take a look at that, you're like, oh wait. Some of you know, if you don't go into autopilot to start filling this stuff out, and you just look at this, you're like, wait a second. There's an x plus 3 on the top and an x plus 3 on the bottom. Those just cross out. Those totally just cross out. Okay? And we haven't seen that happen yet. We haven't seen where a factor in the numerator and that same factor shows up in the denominator. Okay? This is a unique situation. This changes some stuff. Okay, so we kind of have to step back. In fact, it's not going to change the y-intercept or the fact that we don't have a horizontal asymptote, but the other stuff we need to reevaluate. Because once you cancel out that stuff, we don't have a vertical asymptote. There is no vertical asymptote. There's nothing left in the denominator. We're just left with x minus 4. Okay. Once you cancel that out, the only 0 is x equals 4. But because you canceled that out, we get another feature here, another thing graphically. And what we get is something called a removable discontinuity. Okay? That word, and we'll come back to this, that word sounds really fancy, and I don't really want you to worry about it as a vocab word in terms of, I don't need you to know why it's called removable and why it's called a discontinuity. That's something you'll learn in a really different class. All I need you to know is that when you see removable discontinuity, it means there's a hole in the graph. Okay? Literally a hole. Like the graph is going along, going along, going along. There's a big old hole in the graph. And it keeps going along. Yeah. You've never seen this before? This is a new thing. And it's kind of unique to rational functions as far as stuff that you guys have seen. So there's a big hole in the graph. Now, what do we need to figure out about the hole? We want to figure out where it is, right? We want to figure out where If you see, anytime you cancel, you have a hole. Oh, we canceled an x plus 3 and an x plus 3. Where do we think the hole is? Well, if we canceled an x plus 3, the hole is probably at negative 3. But what do we need to figure out about the hole? We need to figure out where it is, and where it is an x and a y. Okay, so whatever you cancel is going to tell you the x of the hole, but you need to figure out the y. Oh, you just take your x and plug it in. Now be careful, you plug in this x into the simplified version. So we're going to plug negative 3 in for x. Negative 3 minus 4 is negative 7. This graph has a hole, a removable discontinuity at negative 3, negative 7. Okay? The last thing I need to say about this is how do you graph a hole? Well, I kind of just showed you, actually, I didn't even mention it. You just have your graph and you draw a little open circle. And that lets the person know there's a hole there. Okay? Cool. It needs to be clearly open, or else they'll just think it's a dot. So it needs to have some kind of open. So on this graph, at negative 3, negative 7, we're going to have a hole in the graph. We're going to have a little dot. Okay. Because there's a hole in the graph, that totally still affects our domain. You can't have, it's all real numbers. X cannot equal negative 3. There's all in the graph. Okay. There's no vertical asymptotes here. There's no horizontal asymptotes. There is this other y-intercept at 0, negative 4. There is this x-intercept at 4. And if you toss this in Desmos, it looks really weird. I'll show you. This is what it looks like. That's just a line. It is. It's just a line. We'll talk more about that, and it doesn't always happen. But what I really want you to emphasize, or really take note of, is at negative 3, negative 7, we said there was a hole. And Desmos doesn't really show you the hole unless you like go directly over it. So if you go to directly where the, it shows you a little open circle there. Okay? But if you look at the graph, it's a really small hole. In fact, it's an infinitely small hole. It's like tiny, 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 tiny hole. And that's because if you plug in negative 3, you have a hole. But if you plug in negative 3.03, you have a point. So stuff really close to there is fine. It's just at that one point, you have this open hole. Okay? Anyway, we use Desmos to help us graph this, and we'd sketch just that ends up being a line with a hole in it. So this is not that crazy. It's just one extra thing. If you have a factor that shows up on the top and the bottom and you cancel it out, that means at that x value, there is a hole, a removable discontinuity. You need to graph it with a little open circle. Okay. Let's do another one. All you're seeing now is that we'll add in a removable discontinuities as one of the features that it's asked about. Yeah? All right, let's rock this out. We'll do this one together. First thing first, factor, 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 factor. Okay. What multiplies to 2 adds to 3, 2 and 1. I'm going to factor the bottom. I'm going to take out a greatest common factor because they all have a 2 in common. That's with x squared plus x minus 2. What multiplies to negative 2 and adds to 1? 2 and negative 1. And I get this. I think you guys are good with the factoring. Cool. After I factor this, the first thing that I immediately notice is, hey, I got something that's going to cancel. I got an x plus 2 and an x plus 2. I'm going to cancel that and rewrite what I have left. Please keep it, like the x plus 1 and the x minus 1 do not cancel. Those are different. Okay. And as soon as I cancel that, I kind of am like, oh, I got to remember that. That means I have a hole. I have a removable discontinuity. Remember, removable discontinuity is just a hole. Where does that hole happen? What happens at -2? What I need to figure out is the y value that goes with that x value. So I'm going to plug -2, not into here, not into here, into here. So grab your calculator. Where's my calculator? -2 minus, or sorry, -2 plus 1 is -1. 2 times -2 minus 1 is -6. So I have -1 divided by -6. I got 0.167. I have a hole on this graph at -2.1. Oops. It's hard to draw them, so you can you got to kind of exaggerate how big they are so that the reader can see. Okay, but there's still other features with this graph. And if I'm looking for the other features after I do the canceling, I should really look over here. So now I'm looking at this guy and pretending like this guy is where I start. Okay. Where are the vertical asymptotes? Well, where's the denominator 0? At x equals 1. Toss that in my graph. Vertical asymptote at x equals 1. Cool. What's my domain? Now be careful. I need to take into account all real numbers. I can't be 1 because of the vertical asymptote, but I also can't be -2 because of the hole. So now when you're thinking about domain, you really need to think about not just the vertical asymptotes messing it up, but also the removable discontinuities. Both of those things kind of feed into what x values you're not allowed to have. Horizontal asymptote, rules haven't changed. This is squared, the bottom is squared, the top and the bottom are both squared. So I'm going to look at the ratio of the leading coefficients. What's in front of the x squared? A 1. So my horizontal asymptote is going to be 1 divided by 2. It's going to be 1/2. It's going to be y equals 1/2. So I'm going to put that in there. Right above the hole. It's kind of hard to see. Zeros. What makes my numerator equal to 0? X equals -1. So I have a 0 in x-intercept at x equals -1. So I'm going to go over to x equals -1, and I have an x-intercept there. Last thing, y-intercept, plug in 0 for x. It's easiest to just plug it in at the beginning. Plug in 0. I get 2 over -4, which is -1/2. So I have 0, -1/2 as my y-intercept. Okay. Put that point on my graph. And this is all starting to kind of fit together. I can use Desmos to help me if I want. But keep in mind that, and this is one kind of weird thing, although this is a hole in the graph, your graph goes through the hole. It goes right up to the hole and then there's a hole in it. So it's never like you're going to have your graph here and a hole over here. That wouldn't be a hole in the graph if it wasn't in the graph. Okay. Your graph's going to have that hole in it, meaning it's going to kind of go to that point. Going along, going along, going along, hits that hole. Those points, comes down here. And it's going to look somewhat similar up here. Toss it in Desmos to confirm, but that's kind of what the graph looks like. Just adding in this removable discontinuity idea, this idea of a hole. I want you guys to pause and give this one a try on your own. Actually give it a try, please. Thank you. I'll give you a little hint if you're really struggling, because the factoring is a little tricky here. Both the numerator and the denominator had a greatest common factor. In the numerator, it was 2x squared, which left you with x plus 2. In the denominator, it was x, which left you with x squared plus x minus 6. Cool. Okay, keep going. Okay, this one was particularly tricky. I get it. But I'll walk through this with you guys. Cool. Okay, so we start up by factoring. Factor. We get this. We do have some canceling here. We have an x on top, or an x squared on top and an x on bottom. Those cancel out. Now it still leaves you with an x on top. You guys know that. X squared divided by x is just x. But we do have some canceling now. And anytime you're canceling, it means we have a hole in the graph. Okay? Let's jump down there right now. Where's the hole? Well, we canceled just x's. So be careful. If you cancel an x minus 5 with an x minus 5, it means you have a hole at 5. If you cancel an x with it means you have a hole at 0. Why? Well, because x is the same as x minus 0. So we have a hole at x equals 0. What do we need to figure out about the hole? Well, we need to figure out where to put it. So we need to figure out the y coordinate of the hole. If you go back and you plug in x equals 0 into the canceled version, because there's still an x here, when you try it, plug in x equals 0, you get 2 times 0 times 0 plus 2 divided by 0 plus 3 times 0 minus 2. You get out 0. That's okay. It just means the hole is at 0, 0. So the first thing I did was go put a circle, a hole at 0, 0. Next, I looked at this canceled version and I said, oh, I'm still going to have some vertical asymptotes. I still have some stuff in the denominator that could be 0. When is x plus 3 0? At negative 3. When is x minus 2 0? At 2. And so I put in a vertical asymptote at negative 3 and a vertical asymptote at 2. If you are getting confused about the order that I am doing things in, it is really up to you for the most part. Okay, there's a couple of things that you do have to do in a certain order, and probably the number one thing is you have to go through the algebra in the order I did. You have to factor, you have to cancel stuff, and you have to look at the simplified. And then you have to remember how things interact. So you need to remember, for instance, on my paper, it'd be good to just draw in this. Hey, vertical asymptotes and removable discontinuities, holes. Those are what control the domain. So you got to find these things before you say the domain. You can't try to find the domain first because the domain is just all real numbers except for these things. So make sure you find the rules kind of in the vertical asymptotes like I just did, and then find the domain. Okay. Next, let's move on to the other stuff. Horizontal asymptote. Horizontal asymptote rules never change. You need to make sure you have these down. The degree, the highest exponent in the numerator is the same as the highest exponent in the denominator. So I just look at the numbers out front. I have a 2 out front here. I have a 1 out front here. What's 2 divided by 1? 2. So I have a horizontal asymptote at y equals 2. Zeros. What makes the numerator equal to 0? Well, x equals negative 2. And I bet a lot of you guys also looking at this are like, oh, and x equals 0. Because this other x here is going to give me another x-intercept. Be careful. Why is x equals 0 not an x-intercept, not a 0? There's already a hole there. There's already a hole there. You can't have a hole and a x-intercept. Like, x-intercept's a point. You can't have a point and a hole. I mean, those are opposites of each other, right? Like, you can't have a point and a hole. So the hole is what's there. Like the hole is what is dominant there. So although it looks like we might have an x-intercept there, we already put a hole there, so we don't have an x-intercept. A similar thing happens with the y-intercept. If you look at this canceled version and you plug in 0, you get 0 divided by negative 6, which is 0. But wait. I already have a hole at 0, 0. Okay, I can't have a y-intercept down here. It doesn't make any sense. I already got a point there. It's a hole. Okay, so in fact, this graph has no y-intercept. We only have this point in the asymptotes. Use Desmos. Okay, if you toss it into Desmos, it looks like this. Fits our picture. We got those 2 big vertical asymptotes there. We got this big horizontal asymptote here. The graph kind of curves there, curves there, curves there. I'm less worried about the picture. Totally use Desmos to help you. I'm more worried about you being able to say any of these features if I ask them. and do this algebra. I know this is a lot. Don't worry. Okay. What I would like you to do now is, is pause, and actually not pause. I'm just going to tell you to do, I forgot, I'm going to tell you to do this problem. Okay? We're going to go over this problem in class, at the beginning of class, next period. Do this problem. I'm going to expect that you've gone through this problem, and I'm going to ask you guys about this. Okay? Cool? All right, this is a tricky one. Start out by factoring. Going to take out some greatest common factors. Give this a try. Cool? We'll talk about it at the beginning of next class. All right, thanks for watching, guys.